NATO project. So we would like to listen to their reports. And Professor Oberhammer, you are welcome.
Yeah, thank you very much for the kind introduction, and many thanks to the organizers of this conference to invite me also this time for showing of our research work. So I'm sharing my screen, and I think you should be seeing my screen, correct?
Yes.
So, okay, so today I will focus on a subtopic in my research group, and that is on antennas. And as we are working with very high frequencies, so this will be focusing on sub-terahertz and terahertz antennas. So as you know from my talk last year, we are working with micromachining. So we make complete systems into silicon wafers by etching rectangular hollow waveguides inside the silicon wafers. So similar to people do microelectronics on top of the surfaces of silicon wafers, we are etching inside the wafers, making three-dimensional structures. I showed that last year already. And I just wanna quickly repeat a few of these things. So basically, we make waveguides inside the wafers. We are also bonding multiple wafers vertically to make larger structures. We have been showing the world's lowest loss waveguides, actually. So these are world record-breaking low losses in waveguides in this frequency range. We also have shown world records in filters. So we have like Q factors of close to 1,000 at 700 gigahertz. The filter work actually is headed by a colleague of mine, Dr. Alexander Glubokov, who did his master degree from U University, and he's an excellent filter designer. And we're also working on phase shifters. So in order to do like phased arrays, you need to include phase shifters also in your system. We also have waveguide switches, because switches are the most fundamental components for making reconfigurable systems. We were working on sensors also, so integrated sensor interfaces in these micro-machined chips. And of course, you need a lot of auxiliary components like power dividers, couplers, and integrated matched loads if you want to do more complex waveguide circuits. And finally, you also need to integrate active circuits. So you need to integrate MMICs or RFICs, depending on the frequency you're working. And of course, in a complete electrical system, you need antennas. And today I'm basically focusing on this antenna part only. Before that, I would like to just repeat also why are we doing this silicon micro-machining for terahertz devices and systems. So what's the advantage of that? So you can make very, very small features, like this cantilever here is only 3 micrometer wide. So it's very, very small. You can etch narrow trenches shown here, so you can do very high aspect ratio structures. So with very small features, you can actually do waveguide-based components to very, very high frequencies. So you can go far beyond 1 terahertz when you have a fabrication technology which can allow you to realize very, very small and accurate features. One of the major advantages is the low surface roughness. So the side walls of these very small features, they have a very, very low surface roughness. And this is typically in the nanometer range. And the surface roughness is the most important factor for getting low losses at high frequencies. So we are metallizing the surfaces. There's a metallization layer on top of the silicon. But the thickness of the metallization is quite irrelevant as long as you have more than a couple of the skin depths. Skin depth is very small at these frequencies. We are talking about 100 gigahertz to 1 terahertz. So the surface roughness is much more important than the thickness of the metallization layer. This is in contrast to lower frequencies where the thickness of the metallization layer is very important. We can do very high aspect geometries, like very, very deep narrow trenches, even with 100 times deeper than they are wide. And we can do diaphragms or membranes, which have 1,000 times thinner than they are wide. So these are very extreme aspect ratios, and they are very good for making high performance microwave devices. And it's impossible to do this in any other fabrication technique. We have very high alignment accuracies. This comes from microelectronics manufacturing, so it's better than 1 micrometer. And this kind of technology is volume manufacturable, so it also can have a high impact on society, because these devices you can manufacture in high volumes. You have a high product uniformity, which means if you manufacture 100,000 of them, they all have the same performance. Potentially, it's also low cost. Now, in prototyping, of course, this is extremely high cost. But if you do high volumes, potentially could reach low costs. So, but today we are focusing on terahertz antennas enabled by this silicon micromachine technique. So I show you a few examples here, and I show you the latest ones which we did first. And these are 500 to 750 gigahertz. So you see we have very high frequencies here. A circular polarized Fresnel zone planar dielectric lens antennas. So this is something very interesting. So it's the antenna prototype looks like this down here. So it's roughly 2 times 2 centimeters. It fits very nice. Actually, smaller than that. It's perhaps 1.5 times 1.5 centimeters. It fits nicely on this waveguide flange here, which is 2 times 2 centimeters in size. And it consists of 2 layers. The top layer here is a Fresnel zone lens antenna, which is a concept very well known in optics and also in microwave engineering. Why not? So this is just a Fresnel zone lens antenna. It has a gradient profile of the width of the rings here. So it's not just a standard Fresnel zone lens antenna. It's a bit more advanced. Because it's optimized gradient. And below it, we have a dielectric polarizer. And the dielectric polarizer we are using to convert the linear polarization, which comes from the waveguide TE10 mode, converting this to a circular polarization. These 2 layers are manufactured in silicon wafers. These are high resistivity silicon wafers, and then put together in a single structure. And that results then in this kind of structure here. And you see that from the feeding point, we have a linear polarized, very low gain, but it's open-ended waveguide here. And then on the output, after this lens, we have a very high gain antenna. I will show you these results soon. Yeah, and the interesting thing, as already mentioned, we are converting from linear polarization to circular polarization, because very often you want to have circular polarization in order to not, for instance, lose your sensitivity on the receiver when you don't match the polarization completely, or you have atmospheric effects which are converting polarization. So I don't go too much into these details, but in many applications you would actually prefer circular polarization over linear polarization, so that you don't have to align the polarization of the receiver, and you're not subject to all the effects of your channel in between, which can affect the polarization. So here's some results from our prototype. This is antenna here. We have a pretty reasonable return loss. You see here, these are measurements from over the whole waveguide band, so 500 to 750 gigahertz. So it's a super broadband device. You have 250 gigahertz bandwidth. Return loss is better than 15, 16 dB all over the band. The black curve here is the simulated, and the red curve is always the measured performance. So we have a very nice agreement between measured and simulated. You see the radiation patterns here. So this is the radiation pattern for the circular polarization in the orientation which it is designed. And this is the polarization in the circular polarization which is opposite. So this was designed for right-hand circular polarization, and of course you have a very high gain. And in the left, if you measure in the left-hand polarization, you would expect a very high attenuation. So we have 30 dB good attenuation of the unwanted circular polarization. You see also here, there's an excellent agreement between simulations and measurements. So the black curve is almost completely hiding the red curve behind it. So it's an amazing agreement, and this shows that you actually can do amazing good radiation pattern measurements even at very advanced frequencies. So we are here like 500 gigahertz, and this here is at 750 gigahertz. And you see also here we have an excellent agreement between the measured and the simulated radiation pattern. So I must say here we have a custom-made antenna measurement chamber which we designed ourselves. And here you see the gain also. The gain of this antenna is like 25.5 dBi. And also here, the red curve is measurement, and the black one is simulated. You have an excellent agreement between measurement and simulation. On top here is the actual ratio shown for the circular polarization. This is just a parameter for the quality of the circular polarization. And it's around 2 dB, so it's also very good. This is a more advanced antenna, so now it's a similar concept, but we have now an even higher gain. So now we have 36 dBi gain, so it's a very high gain antenna. You see here the radiation patterns and 2 different frequencies. And yeah, sorry, this is the same frequency, but 2 different planes, characterized in 2 different planes of the circular polarization. So you see also here this excellent agreement between measurements and simulations. Return loss also here better than 15 dB. And the gain here, that's the blue curve. The blue curve shows the gain here. So we have measured close to 36 dBi gain, simulated 36.5. So we are very close to the simulated values. So it's an amazing agreement. And the efficiency of the antenna in dB is for the most of the band, it's better than 1 dB. And in the worst case, it's better than 1.5 dB. Yeah, this diagram just shows here that if you measure the circular polarization over different angles, what is the gain variation? This is again a factor for how well the antenna produces circular polarization, and you see it's very uniform all over the angles which we measured here. So we have a very nice circular polarization. There's just 2 pictures here about the antenna in our measurement setup, and here a picture of the prototype. So that was a 500 to 750 GHz antenna, and now I show you a corporate FET planar antenna array. This is designed for lower frequencies where you still use metallized waveguides and not dielectric structures. So the basic idea here is that you have a large-scale array consisting of open-ended waveguides, and we have a distribution layer. And from a central feeding point, we are distributing the power to all the antenna elements. And the key point here is that you want to have the same phase front on all the antennas. And you want to have the same losses from the central feeding point to all the antennas. And that allows you to have a very uniform and nice wavefront. This is how it's done. So it's fabricated by 4 wafers. We are etching 4 wafers, and then we are assembling it. Here's some performance. Here's a 16x16 antenna array, 256 elements. We have a gain measured. This is a measured gain of 32.8 dBi, and for the large antenna array with 1,024 elements, we have a measured gain of 38.2 dBi. We are in the frequency range of 320 to 400 gigahertz, and this antenna has an 80 gigahertz bandwidth. The bandwidth is shown here, so this shows the return loss here from 320 to 400 gigahertz, even a bit beyond 400 gigahertz. And we actually, except for 2 points here, we are actually having the return loss even better than 15 dB. And this is the same for the large array. You see that with this very large bandwidth, you have, of course, a change in the behavior of the antenna over the bandwidth. So you see that the half power beam width shown here on the x-axis over the frequency, it is, of course, reducing when you go to higher frequencies because the effective antenna size in electrical size is getting larger for the upper part of the band than at the lower part of the band. You see nicely here down here the 3D radiation patterns measured from this antenna. And at 400 gigahertz, this large array gives you a 1.7 degree half power beamwidth. Yeah, I want to discuss a bit about the scaling. So now we have done the 16x16 and the 32x32 antenna array. And you wonder, well, can you go to larger, like 64x64, 128x128? Yes, you can go larger, and you will, of course, increase your directivity. The larger the antenna aperture, the higher is your directivity. However, at some point, you will not increase the gain anymore. The gain actually will drop at some point when you increase the size for this type of antenna concept. And the reason is that at some point, the losses internally in these large waveguide structures will be larger than the gain increased by the large antenna aperture. And we have done a study here. We compared our technology, so that's the red curve is our technology, as compared to what other people, a Japanese group has done in also using micro machine antenna array. And for their work, the maximum gain can be achieved at 16 × 16 antenna size. But because our waveguide has much lower losses, we could even go to higher array sizes before we are losing the gain, before the gain is dropping. So we have done the 16 × 16 and 32 × 32, but with our technology, we could even go to 64 × 64 or 128 × 128 before the gain drops down. So this shows again how important it is to have a very low loss technology. We have recently utilized these antenna arrays in a collaboration with IEMN in Lille in France. They are experts on telecommunication, and we have utilized this for doing a telecommunication link in which we achieved a world record-breaking 302 gigabit per second in the frequency range of 320 to 410 gigahertz. So this is very new work, and this will be published this year in autumn only. So this is unpublished work actually. So I don't go into the setup here, but we are using a microwave photonic signal generation for generating this very large bandwidth telecommunication signal. And on the receiver side, we are using a real-time oscilloscope with 256 gigasamples. And then we are constructing the different channels. So when you have these large bandwidths, you have to do some channel aggregation methods, and you're optimizing the data rates in the individual channels. So the different channels, because also you have to do it because the antenna has different gain at the different frequencies. So when you have such a large bandwidth, you actually have to take into account that the system has different properties at different frequencies. And for this reason, you typically make sub-channels, and you are optimizing the data rates through these sub-channels. So I don't go through all these details here. But basically, we have accumulated 302 gigabit per second in this roughly 90 gigahertz frequency range, having these 5 channels aggregated here. I show you another example here. This is a leaky wave antenna using the pillbox concept, which was invented by University of Rennes in France. So we have a dual waveguide structure. So it's a multi-wafer structure where we have 2 planar waveguides. There's an input here. There's a parallel waveguide here where the wave is spreading out in this parallel waveguide. On front of it, we have a curved reflector. The curved reflector will result in the returned wave to have a nice parallel wavefront. And we have perforations here, and these perforations will couple the energy down to a lower waveguide in a lower layer. And here the parallel wavefront is traveling back. And then we have a leaky wave antenna array here on the opposite side, that's down here. And this will shape the beam narrow in the longitudinal direction. So we have this curved reflector to make the beam narrow in this direction here, in the X direction as shown down here. And we have this leaky wave antenna array to make the beam narrow in the Y direction. There's a lot of fabrication details here, but I don't have so much time left, so I will skip this. But basically, you need to be able to fabricate very thin membranes for this. So these are really membranes with an aspect ratio of 1,000 to 1. So they're just 20 micrometers thick, but 20 millimeters in diameter. We need to create perforations here for the leaky wave antenna array, like shown here. We need to modulate the size of this perforation for impedance matching. We have the coupling slots here for coupling from the top to the bottom waveguide. In addition, we have a Teflon layer here for slowing down the wave, because in a leaky wave antenna, you have to slow down the wave propagation as compared to a conventional hollow waveguide to get the radiation as wanted. So here's just some measurements. Because it's a leaky wave antenna, you have the possibility to use frequency controlled steering of the beam. So when you sweep the beam from 240 to 290 gigahertz, then the angle is of the main lobe is changing from 20 to 75 degrees. So you have a 55-degree field of view. Unfortunately, the beam, the half power beam width is also changing with the frequency sweep. This is something which we don't want to have, of course. So but it's a very large bandwidth, and you might not want to operate for the whole bandwidth. So we have a measured half power beam width down to 7 degrees. That's the best case here, and the measured gain also here for the best case is 28.5 degrees. Now let's go a bit. The final thing I wanted to show here, that's a more complete front end, where we also integrate a number of other components together with an antenna array to have a micro-machined waveguide beam steering system. And this is used for a car radar project at 240 gigahertz, so quite advanced frequencies as well. So yeah, 240 gigahertz car radar. Nowadays, car radars are working primarily at 77 gigahertz. So it's more than 50% of the radars which are currently in use in cars at this frequency. And the 24 gigahertz car radars will be phased out. So in the future, you will not see many of the 24 gigahertz car radars anymore. But people are already heavily working on even higher frequencies to give you higher resolution. That's the primary reason for it. And also to reduce the sensor size, because you want to have small sensors and not large arrays somewhere on your car. And there's a lot of effort nowadays at 120 gigahertz. So a lot of companies are developing chipsets for 120 gigahertz car radar. And of course, we are doing research, so we go even further. And that's why we did a car radar at 240 gigahertz. And the interesting thing with this car radar is that this car radar is not looking outside the car, but inside the car. It is used for monitoring the people inside the car, detecting where are people sitting. In an accident situation, when you have a crash, you would like to know where are the people sitting, where are the different body parts of the people, like where's the head going, because depending on that, you will inflate different airbags in the car. And a very important application is also a vital sign detection, and here in particular for left child detection. So in the United States, it's unbelievable, but every year there are several babies dying because the parents forget them in their car, and it's getting so hot in the car that they're dehydrating. So this is unbelievable. This is a fact, and in the future there will actually be a requirement for cars to have vital sign detection sensors in the car, which can detect whether people forget pets, like they might forget their dogs also, dogs or cats or their babies. Unbelievable, but this is a requirement in the future. So we have a car radar which is looking inside the car and not outside the car. And terahertz is very suitable for this because you don't need a very large range. So we don't need a 250 meter range. We only need like a couple of meters range, and you need high resolution to actually accurately detect the positions of different body parts, like in case of accident, and also for vital sign detection, need a very high phase resolution. So we did a front-end chip, which is this chip here, just shown on top of a regular waveguide. So it's a 20 times 15 millimeter, 40 millimeter large chip. It has an antenna array here, and it has a couple of interesting features here. So it is designed for a 10 gigahertz bandwidth, 238 to 248 gigahertz. That gives you a high resolution, so you're down at centimeter range. And this antenna array is featuring frequency sweeping beam steering. So that's a very simple method of doing beam steering, similar to a liquid wave antenna. And we also have a method which is called beam shape switching. So we can switch between two different beam shapes. We can switch between a conventional broad beam, which is steering with frequency, and we can switch between that and a notched beam. The notched beam has a null in the center, and this null is can also be swept at different angles. And combining these two beam shapes allows you to get a much better information about the objects you want to detect than if you would just have a single beam shape. So we even could show theoretically that with only having two antenna elements, but the information from these two beam shapes, for a frequency swept antenna array, you can achieve a higher resolution than if you would even have a 4-element antenna array. So this is very counterintuitive because you have a smaller antenna aperture here, But because these two beam shapes give you information which is complementary, you actually can have a better information about the scenery or the objects than in a much larger antenna array. It's very interesting. Okay, I show you a bit in what is inside this chip here. So there's a very complex waveguide system inside the chip, and we can create this broad beam, or it's called a sigma beam in conventional radio technology, or the notch beam, a delta beam. So what's inside here? We have a feeding points here. That's a two-port structure, even though we only use one port in regular operation. We have a switch network here, and the switch networks allows us to switch between these two beam shapes, and this is realized by micro machine waveguide switches. Then we have a magic T. So magic T's are interesting components which allows you to create a signal and a delta signal. And this we are using to generate the 180-degree constant phase shifter, which you need for the notch. So for the notch, you need a 180-degree constant phase shifter. Then we have a delay line network, and that's nothing else than a linear phase shifter, and this is used for the frequency sweeping. So we have a combination of a constant phase shifter and a linear phase shifter. And finally, you have your power splitting network and your antenna array. And this is folded on two waveguide layers, and we also feature amplitude tapering for having a reduced side lobe level. Here's some pictures of the final prototype. So it's a 4-chip device. These chips they contain the different waveguide components, and then it's assembled here to a single chip. And here's the radiation patterns. These are the measured radiation patterns, and over the frequency, because we use frequency sweeping, you have a different radiation patterns generated. This is shown for the sigma beam here, and you see here the animation of the measured radiation pattern. And here you see the same for the notch beam as well. So here you have the radiation patterns over different frequencies measured in our antenna chamber. The center frequency is the one which is circled here. So you have the nice notch in the center frequency, you have the broad beam here, and you also have here the animated radiation pattern. And this was published last year at the European Microwave Conference, and we won the Young Engineer Award of the European Microwave Association 2023 for this innovative work. Okay, that brings me to the end of my talk, and I'm pretty good in time also, it seems. So as conclusions, micromachining is an enabling technology for terahertz antennas and systems. Because you have very small features down to micrometers. This allows you to go to very, very high frequencies. And you have nanometer surface roughness, which is the key to low losses at these high frequencies, a very, very important factor. You can manufacture very complex geometries, which allow you to make very complex and highly compact antenna systems. And yeah, if you consider about the impact of this technology, so you can have a very high product uniformity, meaning, again, you manufacture millions of them and they will all have the same performance. And this is a volume manufacturer technology because this silicon micromachining is utilized for sensors which are manufactured in billions of devices per year. For instance, the inertial sensors in your mobile phone. I showed you a couple of antenna demonstrators. The first one was this planar Fresnel zone lens at 500 to 750 gigahertz. I showed you this corporate fed antenna array with 1024 antennas at 320 to 400 gigahertz. And I also showed you here the measurements which we use these antennas in a telecommunication system, achieving 302 gigabit per second at 320 to 410 gigahertz. I showed you this 220 to 290 gigahertz pillbox leaky wave antenna array, which is, I think it's more interesting from an academic point of view, but perhaps less from application point of view. And in the end, I showed you this 240 gigahertz car radar front end, which features both beam steering and beam shape switching. Yeah, that is the end of my talk. I would like to acknowledge funding sources as well. And thank you once more for inviting me to your conference series. And thank you for your attention.
Профессор Оберхаммер, большое спасибо вам за интересный доклад по исследованиям в терагерцовом диапазоне. Открывая сегодня нашу конференцию, мы отметили, что исследование в терагерцовом диапазоне является одним из приоритетных в мире, о чем заявили организаторы Всемирного микроволнового конгресса, который состоится в мае этого года в Соединенных Штатах.
Professor Oberhammer, thank you for such a comprehensive report devoted to terahertz antennas, and I'd like to mention that this research area is very important nowadays and was named as one of the prime research areas by National Microwave Congress that will be held in the May of this year.
Спасибо вам большое, профессор Оберхаммер, за сотрудничество с нашими специалистами. Я имею в виду, вы назвали Александра Глубокова, это выпускник нашего института, который волею судеб работает в Швеции, работает в вашей лаборатории и разрабатывает вот те интересные фильтры, которые вы показали. Это уже несколько лет, Александр Глубоков, у вас. Сейчас уже второй год находится в ваших лабораториях наш преподаватель, доцент Живков Александр. Александр Живков проводит исследования в области исследования и применения метаматериалов. Это тоже одно из приоритетных направлений, отмеченных в мире. И вы контактируете и помогаете нашим специалистам, осваиваете научные достижения, которые они делаются с их участием.
As well, I would like to say my gratitude for your cooperation with our department, with our colleagues and our specialists. During your report, you remembered about Alexander Glubokov. He is actually our ex-student, and now he works in your institute, and he take part in the filter development that is very important in the field of terahertz antennas development. As well, he works in your department for a few years already. As well, thank you for the cooperation with Alexander Zhivkov, who now maybe for 2 years already work in the sphere of metamaterial development that is as well very important for antennas, and who cooperate with you and now stay in your department. Thank you for this.
И еще, уважаемый профессор Joachim Oberhammer, глубокое уважение и благодарность вам персонально. Это уже третья международная конференция в КПИ, которой вы уделяете внимание, приветствуете, выступаете. Это прекрасный пример сотрудничества ученых наших стран. Большое спасибо и желаю дальше нам плодотворно выполнять эти исследования и проводить конференции совместно. Спасибо.
And as well, at last, I want to say my personal gratitude to you for your cooperation with us. This is the third conference in which you took part and have the time to cooperate with us, to help us to hold our conference. Thank you very much for this. It is really very pleasant for us, so thank you.
Yeah, thank you very much for these very nice and kind words and the nice feedback, Professor Ilchenko. I really appreciate that, and I'm always glad to contribute to your conference, and I'm looking also forward to have more future interaction with you and people from your institute. Thank you very much.
Thank you very much. Thank you very much. Wiedersehen. Наступний виступ нашого партнера